Hello everyone, my name is Eduard Heidebrecht. I'm the CTO and one of the co-founders of RapidRF. Before we start with our session, I would like to thank the Microwave Journal for inviting RapidRF to the RF and Microwave Summit AI in RF. I am pleased to represent our company RapidRF at this summit. During the session, I will talk about the world's first AI RFIC designer, which can deliver tapeout-ready RFIC designs based on your specifications with a single click. If you work in the RF industry and would like to test our AI platform, you can do so by registering via this link. I would like to start with the question, why do we actually need AI in RFIC design? In RFIC development, we are dealing with a decades-long dilemma of balancing cost, time, and performance. But what are the major challenges in RFIC design? The RFIC design process itself takes several weeks to months without any guarantee of success. In this context, the designer's level of experience has a significant impact on the success rate. RFIC designs has many hidden pitfalls that can lead to unwanted oscillations or early failure of the circuits. Both also lead to high overall design costs of RFIC products. The cost of custom IC development can be up to 250,000 US dollar in non-recurring engineering. All of this is further aggravated by the fact that the industry is facing an increasing talent shortage of experienced designers. Since a decade, the enrollment rates in electrical engineering are declining, and the baby boomer generation with lots of experienced engineers are retiring. Due to all of this, the overall RF system development is strongly dictated by the available commercial off-the-shelf components. This is not entirely bad, as it allows for immediate system development and lower overall development costs. But this comes with the price of lower flexibility and therefore high performance trade-offs. Furthermore, there's a strong supplier dependency, meaning whenever a chip is out of stock or obsolete, the developed system must therefore be re-engineered with other off-the-shelf components. On the other hand, custom RFIC part development would provide maximum flexibility, leading to the highest possible performance. Furthermore, it would also lead to full control and independence. We recognize the high demands for custom RFICs in the market, but this could not be realized due to the time-consuming and costly development process. Market analyses also confirm the stated problems. This year, the projected market for RFIC design work is already estimated at 3 billion US dollar, and it is anticipated that this figure will almost double by the end of 2030. Market research has also revealed that the talent shortage is having a significant impact on this area, with many positions remaining unfilled. By 2030, it is estimated that 60% of all new engineering positions remain unfilled, risking the projected market growth. So let's take a closer look at how AI can be leveraged to overcome the challenges of RFIC design. As already mentioned, the RFIC design process is time-consuming. Even an expert-level design engineer needs at least 3 weeks to finish a layout for an LNA or a driver amplifier. Designing a high-power millimeter wave amplifier takes at least 2 months. To reach these timescales as a design engineer, at least 3 years of pure design experience is needed. This is where RapidRF comes in. It enables RFIC design without any prior expertise, which mitigates the talent shortage in the long term. Our solution is an entire AI-driven design automation, providing tapeout-ready RFICs within less than an hour. For that, also no manual engineering effort is required, and all of that is already proven successfully for various RFIC technologies. So, how does all of that work? And how can a customer get his RFIC circuit? On our platform, you can put in your specifications for an amplifier for the supported semiconductor technologies. With a single click, an AI agent takes over the request and starts designing the circuit for you. Our platform leverages a self-developed AI which automates RFIC design. By combining intelligent design exploration with ultra-fast predictive simulation, it enables optimization and innovation at speeds several orders of magnitudes faster than traditional approaches. This unlocks broader design space exploration, rapid iteration, and self-improving workflows. At the end, you can check the design report and download the tapeout-ready design files for your RFIC. As already mentioned, self-learning and improvement are key elements of our development process. We already have a constant growing database of thousands of fully functional RFIC designs in various technologies. The design generation is constantly improving through extensive space exploration. This technology and approach will form the basis for generating arbitrary circuits in the future, including switches, VCOs, filters, and more complex overall architectures. We for sure recognize the high standards of reliability and trustworthiness demanded by the RF industry. Therefore, our solutions provide expert-level designs that can be easily interpreted by RF engineers as shown in this example circuit here. They can also be verified with conventional EDA software if required. Stability and reliability checks are an integral part of the design generation process. This ensures that the designs are functional and tape-out ready. All of this makes the design process for custom RFICs really simple. You enter your target specifications and let the AI do your design. You retrieve the comprehensive design reports and files, from which you can also do your final checks and verifications if you like, or even do individual adjustments. Finally, you can submit the circuit for tape-out. This increases productivity by over 100 times. I know this all sounds too good to be true, but we have already demonstrated this approach multiple times. In mid-2024, as a part of a deep collaboration with Miller MMIC, we benchmarked our artificial designer against a human expert to demonstrate the increase in productivity. This circuit here on the left side was generated and finalized within a single day. The result is that RapidRF was able to outperform the human designer not only in terms of a 10 times productivity improvement at that time, but also in terms of major performance specifications. The shown circuit is a wideband LNA working from 10 to 20 GHz. It not only outperforms the reference design in terms of gain and noise figure, it also achieves a higher operational bandwidth. Our major goal is to achieve first-time right performance with any generated circuit. Therefore, the predicted circuit performance needs to align as good as possible to the measurement. For that, we did several validations for different circuit types and technologies. By March 2025, Miller MMIC had already achieved the ability to design RFICs within a few hours using the RapidRF design platform. This represented a significant productivity improvement compared to the previous year. The two highlighted example circuits were taped out in 150 nanometer gallium arsenide technology from WIN Semiconductors. The K-band driver amplifier operates at frequencies between 17 and 28 GHz with an output power of 18 dBm, while the Q-band driver amplifier is a 5-stage design that operates at high gain between 32 and 52 GHz, which is exceptional for the chosen technology node. Of course, our endeavors are not limited to linear amplifiers and just increasing the speed of design generation. Our goal is to enable the AI-driven design automation of the most complex RFIC architectures, such as millimeter wave high power amplifiers, and to enable the design generation for all possible semiconductor technologies. At the beginning of this year, we taped out our first AI-generated high-power amplifiers using UMS 150 nanometer gallium nitride technology. Both the K-band HPA from 17 to 21 gigahertz and the Ka-band HPA from 27 to 32 gigahertz achieve cutting-edge performance with a measured power-added efficiency of over 30% and an output power of up to 42 dBm of output power. The simulated results show again a good agreement with the measurement result in here. In June of this year, we exhibited at the IMS 2025 in San Francisco, where we launched our AI platform and made our technology accessible to a wider customer base. During the exhibition, we gave extensive live demonstrations of AI-driven design generation. This was all possible because the AI could now perform end-to-end design generation in just half an hour. Currently, LNAs and drivers in MMIC gallium arsenide technologies are available to our customers on the RapidRF platform. Other technologies and circuit types, such as the generation of high-power amplifiers, are currently in the testing phase and will be released in the near future. On the semiconductor technology side, for the general access at the RapidRF platform, the 150 nanometer gallium arsenide technologies of WIN semiconductors are already supported, and UMS gallium arsenide technologies will also be supported soon. By end of this year, the platform will also offer gallium nitride technologies of both foundries. Furthermore, we support customer-specific non-public technologies to which access is restricted to the owning company. Customers in multiple industries benefit from AI-driven RFIC design automation. And application customers, such as RF system suppliers, can focus on performance-driven development and reduce dependencies. Semiconductor companies are less impacted by the talent shortages. They can design faster and increase their overall success rate. Foundries will benefit from lower barriers to entry for their technologies, reduced technology support costs, and the ability to perform rapid technology benchmarking for new processes. The industry today is largely focused on building what you could call the Swiss Army knife of RFICs. The goal is to design components that cover as many frequency bands as possible in order to maximize market reach and reduce the need for developing multiple separate solutions. This approach is totally understandable, as fewer components mean lower development effort and shorter time to market. However, there's a significant downside. By trying to cover every frequency band with a single solution, designers are forced into performance trade-offs. The result is that no single band is truly optimized. If components were instead tailored to address specific frequency bands, the need for such compromises would be greatly reduced, and the achievable performance per band would be much higher. Naturally, some applications do require these large bandwidths, but in most cases, tailored solutions focused on specific frequency bands can deliver far better performance without the compromise of an one-size-fits-all design. Let's take a look at an RFIC reference on the market. The table and graph show the performance of a 6 to 18 GHz off-the-shelf LNA MMIC developed using gallium arsenide MMIC technology. This design covers multiple frequency bands, including the C, X, and Ku band, which are used for different applications in radar, satellite communications, and wireless communications. And please don't get me wrong, RapidRF is certainly able to build these high bandwidths. For example, this 6 to 18 GHz design was generated in under an hour and offers competitive performance in terms of gain, linearity, and noise figure. But what would happen if we generated the circuits specifically for the mentioned frequency bands? This C-band design was generated in roughly half an hour. With its two stages instead of three, it achieves a higher performance, occupies less chip area, and most importantly, has a lower overall noise figure than the reference design. The same applies to the X-band. This design was also generated in half an hour. With two stages, it achieves 26 dB gain and again, a better noise figure than the reference wideband design. And finally, the KU band. This three-stage design was generated in half an hour and outperforms the reference design again in terms of noise figure and linearity. As demonstrated, it is extremely easy to generate RFICs with RapidRF that are tailored to particular requirements. Not only can the performance of a given frequency band be improved, but the number of stages required and, consequently, the chip size can also be drastically reduced. This leads to much higher number of chips per wafer and consequently a higher yield. RapidRF is constantly improving its AI-driven design automation. Our vision is an artificial engineer that can support our customers in developing the perfect solution to a given problem. This includes selecting the most suitable architecture for a given task. For example, the necessity of a distributed amplifier for ultra-high bandwidth, or a Doherty amplifier for high efficiency, as well as selecting the most suitable semiconductor technology node. Furthermore, we are working on collaborations to enable the delivery of custom RFIC designs to end application customers. This includes providing a complete service from tapeout to backend service like packaging to make it as easy as possible for customers to receive their custom chip designs. Our goal is to enable human AI collaborative development, allowing RFIC engineers to focus on innovative architectures and approaches. Ultimately, the AI will assist in the development of entire RF systems. RapidRF is already working on laying the foundations to achieve these goals. RapidRF also has a clear roadmap for its technical services. At the beginning of this year, we worked with our first pilot customers, and by mid 2025, we had opened the platform to a wider customer base for AI-driven RFIC design. Currently, our platform is open to anyone working in the RF industry or involved in RFIC design or planning to be in the future. By the end of this year, we plan to launch public access to gallium nitride technologies for wind semiconductor and UMS, as well as the capability for AI-driven power amplifier generation. By the end of 2026, we aim to empower our customers to integrate their custom technologies into the AI themselves, making this technology accessible to all professionals in the RF industry. Furthermore, our goal is to provide the design automation for every component necessary for full RF front-end development, such as switches and filters and VCOs. We are RapidRF, and we are transforming RFIC design with AI. As already mentioned, if you're working in the RF industry and want to leverage AI for your RFIC design, you can try out on our platform at rapidrf.ai. We will also be exhibiting at the European Microwave Week in Utrecht, the Netherlands, from 23rd to 25th of September. Please visit us there at our booth at number E34. where we will be also doing live demonstrations of our AI design automation. For further information, please also visit our website rapidrf.ai or email us at info@rapidrf.ai. Thank you very much for your attention, and we hope to see you at the next convention.